So I'm going to work out two of the Ampere's law problems here. The solutions are in the homework, but I'm going to work them again from scratch with some voiceover. So the first one is problem 5.14. So here we have a long cylindrical wire, and in part A, we know that this whole wire is going to carry a current I, say in that direction. But in part A, I is on the surface of the wire, and in part B we're told that there's a current density on the interior, and that current density is proportional to the radius that we're at. And in this particular wire we're told it has a radius of A, and we're going to use Ampere's law. So Ampere's law is the integral of B dot dl is mu naught I enclosed, and sometimes we'll compute I enclosed as the integral of j dot dA. So for part A, the cross-sectional view says that the wire here has a radius of A, and if we are inside when we do the integral of B dot dl, and set that equal to mu naught I enclosed. If the current in part A is all along the surface, then the current enclosed on the inside would be equal to 0. And so that would say that the magnetic field strength is 0 inside the wire. And if we're on the outside, say at some radius S here on the outside, then the integral of B dot dl would now enclose some current. The total amount of current enclosed would be this current I. Looks like we're using a capital I in this problem, so I'll switch to capital I. And since I have the Amperian loop as a circle, and the Amperian loop is centered on my wire, I can invoke symmetry and say that the integral of B dot dl is B times 2 pi r is mu naught I, and I see that I get just the formula for the magnetic field of the long straight wire. Oh, I'm using S, so I can make this an S. Okay, so that's my formula for the outside. So when the current is all on the surface, there's no current enclosed by any Amperian loops on the inside, so the B field is 0 on the inside, and then on the outside all the current is enclosed, so I just get mu naught I times 2 pi s over 2 pi s. Okay, so in part B we're told that J is proportional to the radius, so we're going to say that J is Ks. I'm going to take a little detour and find K. Okay, so now when I integrate J dot dA on the whole wire, across the whole wire, I have to get the total current I. So I have a total current I here. So the total current I is going to be the integral of Ks times dA, which is S ds d phi. Phi is going to run from 0 to 2 pi. And S is going to run from 0 to A because the wire has a radius of A. Now what I'm going to do is I'm going to do this integral, and so when I do the phi integral, I get a 2 pi, and the K comes out front, and I integrate S squared ds from 0 to A, and so I get 2 pi K A cubed over 3, so that's equal to the current. And what I'm going to do is I'm going to solve that for the K. So K apparently is 3I over 2 pi A cubed. So that's my constant K, and that's the constant I'm going to put in here. So my current density is 3IS over 2 pi A cubed when S is less than A. Okay, so now that I know my current density in terms of the total current I can use Ampere's law to find the B field. So here is again my wire, and my wire has a radius of A. if I'm on the inside, then I draw my Amperian loop on the inside. And my Amperian loop has a radius, say, of s. And so because my Amperian loop has a radius of s, my Amperian loop is 2 pi s around. So the left-hand side is going to be 2 pi s, and that's going to be the left-hand side whether or not my Amperian loop is inside or outside my wire. And on the right-hand side, though, I'm going to integrate k, let's see here. I'm going to integrate 3is over 2 pi a cubed s ds d phi. Try to clean that up and make that look a little better. And the phi integral is going to go from 0 to 2 pi. And then the important thing here is that the s integral is going to go from 0 to s, because while I'm still on the inside, I only want to use the total amount of current that's on the inside, so I'm only going to integrate out to s. So here I have now b times 2 pi s, the 3, the I, the mu naught, the 2, the pi, the a cubed all come outside. I'm going to get 2 pi when I do the phi integral. And then what I'm left with is the integral of s squared ds from 0 to s. And so I'm going to get 3i mu naught 2 pi s cubed over 3 over 2 pi a cubed. So now if I clean everything up, lots of things cancel out. I get, and then I have the b is 2 pi times 2 pi s on this side. So if I solve this for the magnetic field, I am getting mu naught I s squared over 2 pi a cubed on the inside, which is at s less than a. Now if I go to the outside, again I draw my wire, and my wire has a radius of a. I'm going to draw my Amperian loop outside the wire, and these are both circular wire loop and a circular cross-sectional wire. And so now though my loop is at s and s is more than a, so Ampere's law again is the integral of b dot dl is mu naught I enclosed is mu naught the integral of j dot dA. On this side again, I'm going to have b times 2 pi s. So the radius that I use on the left-hand side always is the radius of my loop. But now on the right-hand side, my formula for b was, or j was 3 I s over 2 pi a cubed s ds d phi. For my s integral, I'm now going to integrate from 0 to a, because the wire stops at the radius of a, and if my Amperian loop is outside the wire, I only want to integrate out to the radius of the wire itself. And so on this side, I'm going to have mu naught, I'm going to have the 3 and the I and the 2 pi and the a cubed. Those are all constants. When I do the phi integral, I'm going to get a 2 pi. When I do the s integral, I'm going to get a cubed over 3, because the integral of s squared ds is s cubed over 3, and then I evaluate it from 0 to a. And so now I see here that all sorts of things are going to cancel out, and this is going to look really stupid when I'm done with it, because what I'm going to get is mu naught I, of course, because the total current I knew was I. So if I hadn't done J correctly, I wouldn't have gotten that. And so outside, B is going to be mu naught I over 2 pi S. And so that's going to be my field strength outside the wire. And I see that my formula for S greater than A and my formula for the magnetic field at S less than A are equal at S equals A, which is an important thing. The field's going to be continuous at that distance. So that's problem 14. Let's turn now to problem 16. So in problem 16, it says that we have two solenoids, one of which is inside the other, but they're turning in opposite directions. So if I do it as a cross-sectional view, I have a solenoid, a big solenoid, that is carrying current out at the top of the page and in at the bottom of the page. And then inside of this solenoid, I have another solenoid for which the current is going in the opposite direction. And what I'm told is that the inner solenoid has N1 on the inner solenoid is the number per length on the inner solenoid, and I have some N2 on the outer solenoid, which again is a number per length. And I want to find the magnetic field in each of three regions. I want to find it inside the inner solenoid, inside between the two solenoids, and outside of both. Okay, so we'll do part 3 first. So if I were to, here by fiat, B is equal to 0, but if I were to think about it from Ampere's law, what I would do is I would draw a Amperian loop out here, and I would note that I enclosed is equal to 0, and so by symmetry and Ampere's law, I would say that, I could use Ampere's law and just say that B is equal to 0 out there. Okay, so now, but let me do this problem in part 1. So in part 1, I'm inside both. So I'm going to draw my Gaussian surface to be like this. So this is my Gaussian surface for part 1. And let me let my loop, I'm going to assume my loop direction as shown with red arrow. Now, the black solenoid is making B field. So the black dots here, the ones on the outside, are making B field that's going to the right. So if I grabbed, I'm going to just for a second highlight something. So if I grabbed this wire right there, if I grab that wire, if I put my pencil on top of that wire and I grab it with my thumb coming up because the current's coming out, and I swing my fingers around, they're going to the right on the inside on that black line. The blue solenoid is making field, or the inner solenoid is making field that's going the other way. So what I'm going to have when I do the integral of B dot dl, I'm going to have B from the outer solenoid times the length minus B of the inner solenoid times the length. And the reason I'm subtracting those is that the outer solenoid's B field is going with my red loop, and the inner solenoid's B field is going against my red loop. There's no B field on the outside part of this loop, and there's no B.dl on the two legs that are perpendicular. And so that's going to be equal to some number on the outer part. They're both carrying a current I, times I, minus some number on the inner part times I. So this is N1 and this is N2. So capital N2 is the number of black wires on the outer solenoid in there, and capital N1 is the number of blue wires in there. And the reason I'm subtracting those is that if the current is going into the page or out of the page, you count them backwards from one another. So here, all I can tell so far is that B outer minus B inner is equal to, oh, this was just stupid. Let me start over. I could do it that way. Well, I could do it that way. Let me just call that B net. Would be equal to the current times little n2 minus little n1, where I've used that little n2 is capital N2 over L, and little n1 is capital N1 over L. And that's the answer they want, right? The answer they want is the net total B field due to both of the solenoids. So B from the outer minus B from the inner is going to be B net, and that's going to be the current times little n2 minus little n1. Now, if I am in between, I'm going to redraw my picture. So I've got my big solenoid, and I've got my little solenoid. What they mean by in between is this region, say right here. In this region right here, there's a B field due to the outer solenoid that's going to the right. But because I'm at that region where I just drew that black line, because that region is outside of the blue solenoid, there's no B field due to the inner solenoid. So the inner solenoid doesn't make B field outside of it, it only makes B field inside of it. So what I'm going to do here now is I'm going to draw my Amperian loop this way, where the outside of the Amperian loop is outside of everything. Two sides are perpendicular, so the B.dl is going to be 0. And then the leg that's running with the B field is between the bigger solenoid and the smaller solenoid. So it's only going to count up the B field due to the bigger solenoid at the place where I want to do it. And so now here, I would have B.dl is mu naught I enclosed, and I would have B due to the outer solenoid, which is times the length, is mu naught N2 times the, just B naught N2 times I, because there are N2 numbers of wires in my box. And so B is mu naught little n2 I. Oh, I lost a mu naught here, right? I should be multiplying by mu naught here, because Ampere's law has a mu naught in it. So here's my B field in that region there. So the outer B field is mu naught N2I, and the inner B field is mu naught N2 minus N1 times I, because the inner solenoid is making B field that's going the other way, so it's canceling it out. So that's how we're going to do problem 516. So the key thing is to think about where you're going to draw those Amperian boxes.